So we are the Newburyport High School sailboat team. Our team name is Seas Today, and our boat name is Speckboat.
It's a bad German boat pun. It means forbidden in German. But they convinced our German teacher to drive us back from the airport, so that's good.
My name is Nick Sundstrom. I'm 17 years old. I'm a junior.
I'm Jake Cole. I'm 16 years old and I'm a sophomore.
I'm Tyler Thompson. I'm 16 years old and I'm a sophomore.
I'm Alec Reduker. I'm 17 years old and I'm a junior.
I'm Mark Doyle. I'm 16 and I'm a sophomore.
I'm Katarina. I'm also 16 and a sophomore.
And we had quite a few other members that couldn't make it here. Four other members that couldn't make it here today.
And actually, everyone on the team but 2 people were new to it this year.
So this is our boat. We decided to go with a kit boat because we wanted to focus more on the electronic side and just get something that worked and functioned. So we went with the Pro Boat Regaza, and we bought it online for I think $600 or something like that. And we made just a couple of basic changes for waterproofing and such. This is the entrance port to the boat. It's the main hatch, and so what we did, we ringed it with window caulking for houses, and we took a aluminum bar and we put it across it just to make sure that the hatch wouldn't come off, because last time we did it, we had some problems with waterproofing and such. And we siliconed the wires to connect to the servos right here into a hole that we drilled in the boat.
And by problems with waterproofing, he means our boat sunk.
And we got 2 Pelican boxes for the electronics, and we Velcroed those in the back of the boat.
Right, so instead of buying a wind vane, because we just bought a $600 or so boat, we decided to CAD and 3D print one using Creo, which I'm kind of new to the 3D model world, so I didn't know, I'm not that experienced, but from what I've learned in my classes, I came up with a design that worked pretty well. And as you can see, we went through multiple different designs, starting at like blocky, weird wind vanes, and we got to more aerodynamic, better wind catching wind vanes. So, and I think we're pretty happy with them. And that's just, those are the CAD files.
Alright, so what you have in your hand there is also a rotary housing for our rotary encoder, which transmits the data that we need to be able to tell where the wind is. So basically, it sticks on top of the mast so that the wind vane,
So when we looked into using an absolute rotary encoder, but we determined that was too expensive on our budget. So we decided to go with a relative absolute quadrature incremental encoder, which gives just the relative location. And we bought several encoders and wanted to find one that had the least amount of friction, so it would be able to turn the smoothest in the wind vane. And so we actually ended up opening the encoders up and fixing the friction ourselves. And we calibrated it with a magnetometer that is in the bottom of the wind vane.
The incremental encoder, by relative we mean wherever it starts, that position is 0, or we use 0 as north, so read wherever it started as north, and obviously that can be correct if it's pointed not at north. It may be, it may not be. So that's what we use the magnetometer for, to make sure that it always read 0 as north. But we ran into another problem with that because we needed the magnetometer actually on the wind vane and wires to come down the mast as the wind vane was spinning.
And the issue with that is that there's 4 wires coming down the mast, and as the wind vane is spinning, that will cause the wires to twist up. So we came up with this solution, which was to have a bottom disc with 4 copper rings stationary on the bottom of the rotary encoder, and then a top disc that would that had 4 copper brushes made out of just desolder, and that would rotate with the rotary encoder, and it would still complete the circuit, but it would allow the magnetometer to rotate and make sure the wires don't get twisted up. In the end, we did not use this because the friction created between the 2 discs did not allow the did not allow the rotary encoder to, in the wind vane to spin freely. So it just seemed more practical for us to get a reading on where north is and then unplug it once we started zero.
It's just a picture of the wind vane together.
So I'm one of 4 programmers. Pretty early on, we kind of split the team into programming team and a hardware team. Only 2 of us programmers are here today. The other ones had to stay back. So our code runs in 4 major segments. There's the autonomous sail trimming, which runs completely separate of everything else. So no matter where the boat is, what we're doing with the rudder, the sails will just stay trimmed autonomously. If it's on a run, they'll completely let out. Even if it's in irons, they're completely brought in, but it's constrained, so they're still completely brought in on a close haul. Sorry. The other ones are an initial check of whether or not it's in the no sail zone or whether or not it's going to be in irons when we're sailing, and that's in the loop, and that's just our initial check. And after that, there's an algorithm to account for rotational error. So if we start to deviate off our course, off our desired heading, and there's also an algorithm for translational error. So if we're actually on the desired heading, but a current is pushing us off that. This is just an example of the initial check. So for an example, if the wind was coming from the top and if it was north, this would be our no sail zone. So our initial desired heading is inside the no sail zone. So we're going to choose a new desired heading that is not entirely. Sorry, I lost a word. So based on whether or not the waypoints on this side of the no sail zone or this side of the no sail zone will sail this new desired heading until we're no longer in the no sail zone, and we check that every 10 seconds. So this is to account for our translational error. This is just completely ignoring wind for this example. Say if the current was coming from here and that was our start and that was our finish, and this was our desired heading, we might actually observe a heading like this. And then we're going to calculate that angle of deviation, which is between these 2. And when we calculate a new desired heading, we're going to subtract that to account for it. And this is just one iteration of the algorithm, but it's running every 10 seconds. So if that was actually our start and that was actually our finish, our checkpoints might be here, until it finally gets a course that's consistent with the current. And you can almost think of the boat itself as a sensor when we talk about it like this, because the boat isn't a sensor, but the GPS, you can't read the current from the boat because the boat is moving as well. So really, all you have to work off of for current readings is how the boat itself moves. And then quickly dealing with rotational error. So that's when we need to turn, not necessarily error, but when we need to turn, or if we're trying to maintain a heading. Depending on how far away our current heading is from the new desired heading, we'll turn the rudder. So if it's a really big angle that we need to turn, we'll turn the rudder a lot until it's matching the desired heading. If it's a small angle, we'll only turn it a little bit so we don't overcompensate a lot.
So due to circumstances out of our control, we were unable to put the boat on the water before coming here. But we did test a lot. We did do a lot of testing with the wind vanes and the rotary encoders prior to coming here. And so yeah, we were able to test just like with the RC control to like on land before coming here. And other than that, it was pretty much going for it. We ran into several problems while we were here. The first, when we arrived here in Newfoundland, we didn't have our boat because it was never put on the airplane we flew here in. So luckily we got it like within 24 hours, and we were able to still make it to the competition.
Well, when we first put it into the water, we were going for the fleet race, and the instant that we got on the boat to go out to the fleet race, our stays broke on our mast, and the RC controller broke. So we had to bring it in, but we fixed the stays. We used similar gauge wire, and we crimped them to hold the mast up, and we kind of super glued the RC controller. So yeah, and then from there we had problems with the sail winch. The kit boat that we had came with a servo for the sail winch, and we ordered an extra because we figured we might need it. And little did we know, while he was testing with the extra that we had ordered, the sail winch inside of the boat was completely different from the extra that they sent us. So the servo inside the boat didn't respond to our programming, so we had to switch out the servos, which took a lot longer than it should have. And we had to fix there's a housing for the servo to keep the wire, the rope on servo, and because the servo was so different, the casing didn't work for it, so we had to fix servo placement to make the casing work. So it took a lot longer than it should have.
So, as any programmer here can relate to, things rarely go the way you want them to. So we did run into a lot of problems coding, especially because we are almost entirely self-taught. I think two or three of us have a little bit of class time coding, but apart from that, it's stuff that we've done in our own time. And so when we do run into a problem, we run through a pretty standard process of debugging and commenting out certain functions and maybe testing out different hardware to see where the problem really is. Oh yeah, I'll talk about that. So also another issue we had when we got here was frying electronics. I by accident missed a wire and plugged in 5 volts to a compass with no ground, and that fried it. Luckily, we had an extra, very luckily, so we had to take apart the wind vane to put that in, and we ended up just covering it all up with more window caulking.
Yeah, we actually had to use window caulking to balance the wind vane because it was not quite balanced, and also we use Arduino entirely.
Oh, completely forgot to mention that. Yeah, yeah, we ran entirely off of an Arduino. We used an Uno. We tried to use the Do, which is the new one, but some of the libraries we were using weren't compatible with it, so we ditched it because we didn't really have time to learn something completely new. It was really hard to swap out the functionality of, say, a Pi or a BeagleBone for the Arduino, but it's something all of us had experience in, and we thought that was a lot more valuable than learning something new, even if it had more functionality, just because we could get something that actually worked.
And we were funded by the Newburyport Education Foundation.
Yeah, our teacher, Miss Ledbeater, is really, really good about organizing and getting us money and driving us places.
Buying food.
Yeah. And hot gluing and soldering.
That's it. Any questions?
Yeah.
Did you guys have a class, or did you do it all after school?
Entirely after school. And I mean, a lot of it wasn't even done after school. I can think of quite a few nights where we stayed up till midnight, walking around outside with a GPS and a laptop coding. So I mean, yeah, it was almost entirely on our own time.
How's your algorithm working in practice?
In practice, the sail trimming algorithm is working well. And to be honest, we haven't really got a chance to test all the other stuff. One of our programmers who did a lot working with the GPS logic couldn't come, so there's some stuff missing. Some code that I'm having a tough time reading, and so the GPS logic it's hard to tell yet because the code isn't entirely complete. But yeah, the sail trimming's working really well, and I know that the upwind sail checking is working really well. But I haven't, and also due to hardware problems and stuff, we haven't really been able to test the other parts. All right, we've tested them on a conceptual level, so the code itself hasn't really been.
It looks like you've encountered a few obstacles along the way, and
Yes.
you've learned, no doubt, a lot about finding fixes and finding workarounds and so on in the field. That's a valuable lesson to learn. Now, you mentioned your teacher, who we appreciate having here, and I was just wondering if there are any other resources that you were able to utilize other than the internet and self-teaching.
A little bit. We had a local programming company, Muzzy Lane, came in for 2 hours one day just to kind of sanity check our program,
Okay.
and they were really helpful. We haven't been in too much contact with them after that, but it was really helpful just to talk to some professionals who gave us, this is what you do. This is what you want to do, and we think it's going to work, and here's how you're going to do it, which was a really big step for us because we spent so much time conceptualizing, and then when it came time to actually put it into code, we really had a really basic understanding of how we were going to do that.
Also, besides that, she didn't really know a whole lot about like sailing or robotics, but she was very good at organizing the whole thing. So
Good.
yes.
Wow. You need good project management.
One other thing. I think it was mentioned before, but only myself and one other team member have had. We did sailbot before, so we had a little bit of experience, and only 3 of us had sailing experience as well.
Hold on.
So I found your presentation is great. I'm able to understand everything that you've done. So obviously we mentioned we used a magnetic shaft encoder versus your encoder. We have the same problem with wires running up the mast, and they're kind of complicated. Can you think of a reason, a compelling reason, the difference between a magnetic encoder versus your kind of a relative encoder?
For us, it was cost. I'm not sure how much yours cost, but
About $49.
yeah, ours
Ours
was
the
$3.
one we ended up using was $1.50.
Yeah, so yeah, $1.50 and a magnetometer for
So it's
$13.
a significant cost savings.
Yeah.
And you could practically throw them away when they break.
Yeah,
Yeah.
We ended up bringing like 20 of them.
Yeah, there's
Yeah.
15
So
here.
yeah, 15. So
That's a big thing because we choked on the cost of the encoder.
yeah.
We needed a spare, and that
That's-
was like, can we really afford a spare?
Honestly, the magnetometer in the wind vane was kind of a hack solution, but it didn't really have the money to go for an absolute encoder.
Well, I'll tell you how we solved that particular problem. We just simply set the boat north, and we set the trim on the wind vane south. And we said, whatever it reads now, we're just going to subtract that from whatever it reads of the next reading. And
Yeah.
So it doesn't self-adjust on the water, and whenever it's blowing around, we just got to recalibrate.
Yeah.
But that saved us from having to mess with all that extra cost and labor and craziness of trying to calibrate.
Yeah, I just felt like I did think about doing that, but I felt it was just the nature of having it in an autonomous sailboat. It needed to be kind of calibrate itself.
And I agree with you 100%, except for there are so many other things that go wrong.
Yeah, and there was like
But I like that you're thinking that it
discs,
does
for
self-calibrate
instance,
itself.
didn't really work how we wanted them to.
Just a level of complexity. A great presentation and a good vote, and I wish you the best of luck tomorrow.
Thank you very much.
Just a general question about the wind here, I guess. Do you find that a big challenge? What do you think that's what maybe broke your mechanical part?
The winch? No, it didn't. The winch didn't break. It just didn't. It wasn't.
Communicate.
It
It
wasn't
couldn't
compatible.
communicate with
It
the
wasn't
Arduino.
compatible.
Yeah,
with
the-
our
the-
program.
The winch in the boat was a continuous rotation servo, and the winch, the extra winch that I was testing with, was not a continuous rotation servo. It was a standard servo. So it just it did not make any sense to trying to recode it. So we just replaced them. It, like you said, it took a lot longer than it should have.
But once we did, it ended up working really well.
So do you read data back from your servos? Or just, yeah, that's it, you just tell it where it's supposed to be, and if
Yeah.
it doesn't go there.
So be it. Yeah.
Well, very, very impressive project, and congratulations to all of you. Absolutely intrigued by the level of detail that you're going into it as high school students. So compliments to teachers and everyone. Would you be interested in designing and building your own boat then?
Yes,
Actually,
we're-
we were.
No, yeah.
Actually, we were at the beginning of the year. We were like talking about maybe doing a 2-meter boat, but we decided that it would probably. We didn't really have all of the resources necessary to actually make it, but we're really interested in maybe making it a class next year and being able to make a 2-meter boat.
Okay.
I remember specifically walking into the classroom one day, and we were thinking about doing a 2-meter. And I came in and I had all these resources online. I was saying, okay, like here's this and here's that, and I wanted to do a catamaran with a hard sail. And then I tried my hardest to get everyone on board. And then it came time where people were like, okay, maybe, but let's try and build it. And then it was, oh, what are we gonna do now? So I think if we were to build our own boat, we need some outside resources. We really don't have the experience or the tools for it at our school.
And also, 2-meter boat would have been much harder to get here.
Yeah, of course. Yes, I understand that. Yeah, I just want to get a sense. I imagine that you may have to grow the team a little bit if you have
Yeah,
as well, and so on. Well, okay. Good luck with it. Fantastic. Okay, thank you.
Thank you.
So we'll take another 10-minute break. Get up and walk around.
Sorry.